Hello, everyone. So today I'm with Hazel Jackson from the University of Michigan. We met at SSC. What does ASSC stand for again?
The Association for the Scientific Study of Consciousness.
Right, right. And she gave a world-class presentation, Criticality, there. So we became good friends. And today we're going to chat about criticality. So please.
Hi, yeah, so I made a presentation about criticality for you guys. And so in this talk, I'm going to talk first about what criticality is and then talk more so about its broader relevance. Then I'll give a little bit about measuring criticality and then some studies that apply it to animal studies, consciousness studies, and artificial intelligence. And criticality is interesting to me because I'm a neuroscientist and we use criticality in the consciousness studies application. So let's talk about criticality. So as you know, a
But
static
Hazel,
network,
sorry. Like,
what?
if I may, why did it just kind of was criticality what you just went into the lab and they were doing? Were you kind of interested in it before, or were you just interested in neuroscience in general? Was there?
Yeah, no, that's a great question. For me, I was interested in consciousness, so I went to the University of Michigan to study consciousness because they have a center for it, and there's not very many centers for consciousness science in the world. So I was excited to go to Michigan. And then I joined my lab, which is a computational lab.
Mhm.
And my PI, whose name is Dr. Unchal Lee, is really interested in criticality. And he's really interested in criticality as a way to help explain conscious experience. And so I picked up this method in his lab
Do you know why
and
he's
learned more
interested
about
in?
it. Yeah, why he's interested in it?
Yeah. Why does he think
Because,
it's important?
yeah, I mean, I'll talk. I actually have a couple slides about that later in the
Okay, okay.
presentation, but he thinks it's important because um, of the advantages criticality brings to a system. So, and also with experimental data that sort of is supporting this idea, which seems to show that criticality and consciousness are correlated, and criticality as a fundamental principle can help explain why certain brain dynamics lead to consciousness while others don't.
Okay.
So, is that helpful?
Perfect.
Okay. Yeah, so to understand criticality a little bit more, so when I say dynamic network, as we know, in a static network, there are different nodes that are connected to each other, but there's no change in the status of the network over time. Whereas in a dynamic network, these connected nodes change their state as we travel through time. And so in these dynamic networks that have two different states they could be in, so like in a magnet, we can think of, in a ferromagnet, we can think of the magnetized state versus the not magnetic state, or in the brain, we could think of neural amplification and decay. When the system transitions between like state one and state two, there's this point in the middle, which is the point of the phase transition, which is called the critical point. And these critical points are interesting because they convey functional advantages to the network. Hold on, I think this is making noise. Maybe not. No, it's not. I'm not sure. Anyways, and so criticality brings functional advantages to the system, and these advantages include optimal information transmission, efficient signal propagation, maximal information storage, computational power, and dynamic range. And also, the system is more sensitive to perturbations. And so, if we think about criticality in the context of a ferromagnet, which I mentioned earlier, in the subcritical state, like if you're thinking about the metal and the atoms in the ferromagnet, in the subcritical state, this is the magnetic state where all of the spins in the atom are aligned. So each of these dots in the screen here we can think about as the direction of the atomic spin. And so if they're all the same color, that means they're pointing in the same direction, and then you can see that there's the occasional spin that's flipped like the opposite way in the subcritical context.
Hmm.
On the other hand, like in state two, we can think in the supercritical state where, this is like when the metal that's for the ferromagnet is hot. All of the spins are like every which way. So there's not very much order in the spins. And so the the metal is no longer magnetic because there's not enough order among the atomic spins. However, if we're looking at this critical state, we have a more variability between the different atomic spins. And if we're thinking about these spin flips, which are occurring within the critical state, we can see some of these properties here. And so to give you a little bit more intuition about some of these properties, we can look at this example that's demonstrating maximal information transmission.
Mm-hmm.
And so in this example, we're going to play a guessing game, which is trying to figure out what the input to the network was based on what's happening at the output layer. So we can think of these series of nodes here as a feed-forward network where there's input on one end and the information is transmitted through the network to the output layer. And us over here, the observer, needs to figure out from the output what the input was. And so if we're in the subcritical case, we're going to see a lot of decay in the signal. So playing this game is impossible because the input signal never reaches the output layer. And so the signal always decays, and so we never see anything at the output. So we can't figure out what was input into the system. On the other hand, in the supercritical case, the signal is amplified. And so if we're on this output layer, we also can't figure out what the input was because either none of the nodes are activated or every single node is activated. So we can't figure out what the input was. However, in the critical state, we have good information transmission. And so we're able to see what the input to the network was. It's transmitted efficiently through the system to the output layer. So if we're playing the guessing game at this output layer, we are for the most part able to figure out what was input to the system, or able to figure out with high probability what the input was.
Mm-hmm. Yeah, that's very intuitive, yeah.
Yeah, okay. And then any questions on that slide?
From the previous slide, what I'm seeing is that, and correct me if I'm wrong, I'm sensing it's almost like you need a sufficient amount of like the right amount of activation and like differentiation. The signal needs to not only get across but be sufficiently differentiated such that you can get the information transfer. And that means like each random sort of it needs to have its, what do you call it, needs to be encoded sufficiently differently so that you can decipher it, decode it, but you need to get across also. And it's kind of that balance, no? And also like the fact that in the supercritical one you have this vertical line going across, it's like the nodes beside each other activate each other. Is that the correct intuition? So if it's super critical, you don't get this kind of differentiation that allows you to decode because they all just like light each other up.
Yeah, and so a way to think of this is, so remember we're looking at this as a feed-forward network. So each column is a different time step. And so we start at T0 at the input layer and then like T+1, etc. through the network. So what we're seeing is the previous nodes causing downstream nodes to light up, not like lateral nodes.
Okay.
And so what we see in the supercritical case is one lit up node can light up multiple downstream nodes. So we're going to have this divergent amplification effect because one node can lead to the activation of maybe 3 in the next step and then 6 in the like step +2 and then like etc. And so we're leading to this everything's lit up case in this supercritical state because the previous nodes are likely to light up more than one downstream node.
Okay. So it's like the x-axis is time, really. Is that correct?
Yeah. Yeah, the x-axis is time.
Okay.
Yeah, and then what this little sigma here means is this is actually a measure of criticality called the branching parameter. And so in the critical case, we can see the branching parameter equals 1. And this means that on average, a single node will activate one downstream node. And so that's why we have good information transmission because like we're not getting more nodes lit up along the way and we're not losing them as we go either. Whereas in this supercritical case, we have a sigma greater than 1, which means that on average, each individual node lights up more than one downstream node, so we get the blow-up effect. And subcritical is obviously the third option where sigma is less than 1. So on average, less than 1 downstream node is lit up from the current activated node.
Got it. Okay, blow up effect is the keyword I see. So it's like blow up versus like this vanishing, what do you call it?
Like
Thing.
decay.
Decay.
Yeah.
Okay. Cool.
Yeah.
Cool.
Yeah. Yeah. Whereas the critical signal is more stable because it maintains its fidelity over time.
But this is the point I sense was that not only do you need to avert either decay, excessive decay, or excessive blow up, you need to be able to have like a signature for each input, which is unique and allows you to get the information. But I guess that's implied, huh? Okay.
Right. I mean, I guess the way that this critical network is set up is if, like what I'm hearing from you when you say signature is you maybe want to know like which nodes were activated, not how many nodes were activated. Is that
Right,
right?
which nodes are right, exactly. That allows you to decode and it gives each input a unique or sufficiently unique output so that you can decode it.
Yeah. And that's a good question. And so in the way that this network is set up, like since it's like linear, right?
Hmm.
So it's likely that just like the node like that corresponds like if like node A like lights up the next row, it's likely it'll light up node A again because it's just one downstream step. But also in this example, like you can see even in this like cutout picture on the left, we are measuring that there were 3 input nodes, but the 3 that we're counting downstream are not the same 3. So this specific example maybe isn't getting at the question you're asking, which is, or the point you're bringing up, which is the identity of the nodes. It's more
Exactly.
quantity in this specific example. But in real life networks, there's, likely, like if that's a thing that's beneficial to the survival of the system, right? There should be pressures that support these identitive markers.
Quality. Yeah, cool.
Yeah.
Okay.
Yeah. And so talking about maybe some specific relevance of criticality, like what might lead you to be interested in it. We know that criticality is a universal physical principle, which is interesting because this means that criticality can occur in any dynamic system regardless of the substrate of the network. And so, right, so criticality can occur in magnets, as in the example we saw earlier, but also fluids and brains and artificial intelligence networks, even financial markets, among others. And in an early paper by Back, Tong, and Weisenfeld from 1987, they found that dynamical systems with degrees of freedom will naturally evolve into a self-organized critical point. And so this is interesting because it seems that these dynamic systems will naturally evolve into the critical state as sort of like an attractor dynamic.
Okay, I don't mean to keep butting in, so let me.
No, it's great. Yeah, please keep.
On one hand, this makes you care more, but on the other hand, it also makes you be like, okay, so this is almost like a regular phenomena across substrates. Why identify the brain as such? Why
Yeah,
care?
that's actually a pretty common criticism of criticality is like, oh, what's the explanatory power if it occurs in everything? It seems so commonplace. And so that's actually something that I have in this next slide is the way in which it's applied to different systems is interesting, I think. And also it's maybe an idea that criticality can occur in any system, but the effect of it is different depending on the system it's occurring in. Right? Like in a magnet, in the subcritical state, there's magnetism, and in the supercritical state, there's no magnetism. And so, at the subcritical or at the critical point, we get maybe different dynamics than we would in the critical state in like a brain. Like brains aren't magnetic, so we aren't gonna get. Well, okay, they are sort of, but like you can't stick a piece of metal to your brain and it'll stick there. You know
Sure,
what I
sure,
mean?
sure.
Yeah.
Okay,
Yeah.
cool.
Yeah. And so I found like one of the reasons I'm interested in criticality is because I find these studies to be very interesting. And so what I have in the presentation a little bit later is a couple different example studies that are looking at this. And so maybe if we look at those studies in more detail, we can think more about this question you're raising about like why I care about criticality. since it's universal.
Hmm.
And so before we move into that, I wanted to just talk briefly about measuring criticality so that we have a little bit more of a handle on like what these studies are doing to be able to find out if their system is critical or not. And one of the, I think, limitations of criticality studies is that there's no gold star method to measure criticality. So there's a lot of different metrics that can get at criticality, and different metrics are better suited to different data types. But to be able to conclude that your system is critical, multiple metrics need to agree with each other to lead to the conclusion that your network is critical. And so when you're doing this analysis, when people do this analysis, to add confidence that their system really is critical, it's helpful to compare their results to surrogate or scrambled data to see what they get. And so if the system really is critical, the surrogate and scrambled data should disagree with the conclusion they got from the raw data.
What does that look intuitively? I feel like that makes sense, but what does that look like?
Like surrogate scrambled data or just across the board?
Yeah, what does surrogate? What does it mean? Like, so I'm hearing what I'm hearing is that surrogate or scrambled data is the kind of control that you can use, like an
Yeah.
ablation study. But what might that look like?
Yeah, like for example, in the brain, like if you're going to measure criticality, you might be curious about neuronal behavior across time, right? And so if the brain is critical, then the behavior in time should give you the answer criticality when you do your analyses. But if you wanted to scramble your data, you could take all the same amount of activation, but shuffle the order that it's occurring in time so that it's going to break up some of the dynamics that would give you the answer criticality
Mm.
in the first place.
Okay, that makes
And
sense.
so, yeah. And then, again, one, one property of criticality, for example, is that your system will follow what's called a power law, which means it's linear in like log space. And so power laws are really similar to like exponential functions. And so like one, it's not a surrogate or scrambled data, but it's a control is like you can control your results and see whether like power law data fits better or exponential fit data fit or like an exponential fits better. And if you get the same confidence in your fit, then that would decrease your conclusion that your data is critical because it's equally likely to be an exponential fit than a power law fit.
I see. Okay. Okay. Is it that big of a difference? The fact that something would be log versus exponential, is that quite significant?
Yeah, I think it's significant because, like, theoretically, it's supposed to be power law, and if it's not power law, then it means it's not like it's not meeting the expectation of this measure of criticality, right? So, like on this slide, for example, I've listed several different measures of criticality, and if you're looking at your data and you're trying to figure out if your results are close enough to the target answer for each of these different metrics. So with power law fits, like power law fits means your data should be power law fitting. And given that there's an amount of error, like anytime you fit any function, there's going to be some error. And so, you're going to get error with your power law fit, and it's ambiguous to determine how much error is too much error with your power law fit. And so one way to help control for that is to see if an exponential fit is better, because an exponential fit is a different fit. And so if it's equally likely, then it might mean that there's too much noise in your data to be able to tell the difference. Because in data, you can tell a true power law from a true exponential. And so if you can't do that in your data, then you don't have enough data points, for example, would
I
be a
see.
conclusion. Right? Like if you're doing like a fit for your data, like maybe I can draw a little graph here. Let me do pen. So if we have this as our graph here,
Hmm.
and we have like a single data point, and we want to fit, the distribution to this function. You can fit any distribution to this single data point because anything is going to go through one data point,
Hmm.
right? Um, and then if you add like a second data point, now you're going to get more confidence in your fit, but still like multiple distributions fit, like a linear distribution fits, but also like a quadratic distribution fits, and also maybe like you can get You can fit all kinds of stuff to these two data points, right? If you're asking
Hmm.
for this kind of fit, you can get the answer that it fits in all cases.
Hmm.
So, just trying to control for that by looking at alternative hypotheses is a good way to be more confident that you're really seeing critical data rather than data that can just fit given the quality of your data.
Okay, that's very intuitive. And what you're saying is that maybe one of the gold stars is this notion that it has to fit log log, but somebody decided that, right? Or is that just a signature of criticality regardless of substrate across the board in dynamical systems?
From my understanding, it's a substrate from physics, like physicists who described criticality initially.
Got you.
But I'm actually, yeah, I maybe would interpret that with a caveat. Like as someone with a neuroscience background, I'm coming into this physicist field, and so papers that I've read talk about this like definitively, this power law,
Hmm.
idea definitively. Um, but I haven't looked at papers like before like 1989, for example.
Yeah. Okay.
Yeah. And so on this screen right again is I just wanted to include some different criticality metrics just so you can kind of get like a sense for like this isn't even all of the possible metrics, right? It's just to get a sense of like some of them that exist.
Hmm.
And so it's good to try to look at what you're saying. And so maybe I'm not going to talk about what each one is, but I did include this example to help visualize one of them, which is scale invariance, partially because I think the videos are fun and it's sort of quick to explain. And so if a system is critical, then it will be scale invariant. It should be scale invariant. And if it's not critical, then it won't be, obviously. And so thinking back to our magnet example, in the case where all of the spins in the ferromagnet are random, like it's every which way, there's no order, then when we look at the magnet, it changes the like visibility of the magnet changes based on the scale. Maybe to help make this more sense is if we start in the critical state, which has scale invariance, in this black and white box in the middle, we can see the different spins. Spin being like the white spin versus the black spin.
Hmm.
And then if we move into the video that's showing scale invariance, now like green is one spin and red is the other spin. As we zoom out, when we get a wider field of view when we look at our magnet, it should look roughly the same. Like the distribution and number of spins of each type should be relatively indistinguishable when we look at different scales. But you would see like in the disordered phase that I mentioned first, like as you zoom out, your picture changes, right?
Yes.
And the same thing happens. Go ahead with the order. Go ahead. Sorry.
Yeah. Well, okay. So this is very intuitively pleasing. So I like it. And to tie it back to the magnet idea, the point is the word you use is distribution and number, right? So that remains invariant regardless of the amount of coarse graining you do. So what you're saying is if you can start lumping these magnets, and as you lump is like roughly moving outwards, you have to move outwards at the rate at which you do these lumpings, but you get the same picture. Is that how you bridge the magnet with the with this visual? Is that correct?
Yeah, in the critical case, you get the same picture as you do the
Yeah.
lumpings.
Okay.
Right, but obviously when we do the different ends, like the subcritical versus supercritical, we get different pictures as we change our viewing lens.
This is a purely local. I guess it's not a local phenomenon, is it? What is this? Why? What?
It's more like a global
Yeah.
or global within the region. Like it should apply to the whole set that you're analyzing, right? So if your magnet is critical, then the whole magnet is critical.
Right. So it applies. But that's the point of scale invariance. It's both local and global, and they both hold the same characteristics or properties across the board.
Yeah.
Yeah.
But I
Okay.
suppose like if you had a case where, you're looking at like I don't know, an object that has good, you have like a metal object with good insulation breaking apart different metal pieces. Like, can you imagine, like, if you got like a metal rod with like a piece of rubber and then a metal rod, piece of rubber, but like a metal rod. So you got 3 metal rods, right? Like, you could, in theory, make it so that like the 2 metal rods on either end are critical, whereas like the middle rod is like different because you can heat up the middle rod without it traveling to the end rods. Like if you're insulated enough, you can have, I would imagine, zonal criticality. Right?
Understood. Okay.
Yeah. And so, okay, so let's talk about some examples. And so first we can talk about this application to animals. And so, Ernest, I'll let you decide how much depth we want to go into on the details of each study.
Mm-hmm.
So let me know. And so I have 2 different studies in rats that are talking about this concept of self-organization and criticality. If you recall from an earlier slide, it was mentioned that dynamic networks will settle on this critical state. And so we have 2 experimental examples, this page and this page, talking about a manifestation of that in the rat brain. Mm-hmm. And so we have these here, and we can come back to them if we want to go into some details. We also have this idea of the critical brain hypothesis, which posits that mammalian brains, or brains in general, evolved to operate at the critical point because it provides those functional benefits we talked about earlier, like maximal dynamic range, information transmission, and representational capacity. And this hypothesis is stated because these functional advantages are instrumental to healthy brain function, and deviations from this brain criticality should cause deviations from normal brain function. Okay, and so we have...
Okay. Yep, so you have...
One more time?
I'll let you finish, and then I'll ask.
Oh, yeah, okay. I was just going to say, we also have, like, this slide, which is talking about, some support for the critical brain hypothesis, which is from a review paper that's looking at a synthesis of studies across different animals and comparing like the wakeful state, which is near the critical point, with these other altered states which deviate either towards subcriticality or supercriticality, depending on the type of state.
Can you see me or no?
No, because I only have one monitor, so...
It's okay. I just thought it'd be cool if instead of me randomly butting in, I could kind of raise my hand, and then that could allow us to, but maybe for another time. You feel me? Because that way then you could kind of be like, okay, here's a question, let me round it out. But it's okay. We don't have to. Maybe next time.
Yeah, it's actually it's
okay?
fine, I think, for you to button. Yeah, it's not messing up my flow.
What if I raise my hand? Can you see when I raise my hand?
No, I can't see you at all.
No, I mean there's like I can click a button that does hand raising.
No, I can only see my PowerPoint slide. Is maybe a better way to answer your question.
Should I sneeze? That's okay. But anyways, the question I wanted to ask was, okay, so the slide before this, right? You say the word evolved, and
yeah.
I'm hearing like 2 things, right? Because on one hand, this is, I'm assuming they're saying, critical brain hypothesis, we're folding this into the Darwinian story. Given that there are all of these functional benefits, it makes sense that natural selection would select for critical things. But on the other hand, I'm hearing that these are self-organized systems, right? So this kind of evolution can be considered in that sense, that the dynamics of the system is evolving towards, right, this critical state. And I'm assuming in this one, it is certainly the Darwinian story, but do you get what I'm saying? There's kind of a blurring when you use this kind of language. Like, where do you stand here? Is there anything interesting to be said about this?
Yeah, I think that's good to call out the precision of language. I feel like that's really, especially as a consciousness researcher, I think it's really important to be clear about what you mean, right? So, I definitely use these words without thinking about it. But I suppose to answer you, like now if I do think about it, I think, I suppose, you could think of maybe evolution pushed, dynamic systems to evolve within animals, right? Like it pushed the brain to evolve as a dynamic system.
Or it's selective,
that then therefore
right?
could, yeah.
or
Right.
it's selected
Yeah, I mean,
for,
yeah.
but it would be purely based on the functional benefits, right? Because it clearly like the environment isn't, from a Darwinian selection perspective, helping us be more critical or remain in a critical region, right? It's just like, oh, you're more critical, you can do more stuff, you live,
Yeah,
right?
right.
But then the self-organizing story is kind of like all dynamical systems, or you said, you mentioned earlier, there's this like general characteristic of these complex dynamical systems to evolve, to transition towards a critical state. I don't think this is necessarily a very interesting point. It's just, you know what I'm saying? There's an interesting thing here. It's not a profound point, is what I mean. But yeah, I know.
Yeah, I guess, I mean, maybe what I'm hearing also in your question is there's two different time scales we're
Mm-hmm.
thinking about, right? Like in like the present moment or within like a short amount of like a short time window, right? If you have a dynamical system, it's supposed to evolve to the critical point based on the theory I presented earlier, right?
Right.
Within like a short time scale. Like that's what a dynamical system will do. If you have a dynamical system, it's supposed to do that. But from the evolution scale, which is much longer scale, like maybe what I was trying to suggest is that evolution selected for the development of dynamical systems within
Yeah.
animals, which
Yeah.
was brains.
Yeah. So the reason I bring this up is because that's what when I hear the critical brain hypothesis, and you're saying, when I read some of these papers and they're saying brains evolved,
Yeah.
they're directly tying it to this functional Darwinian selection story, which is a big hypothesis, right? They're saying this provides survival benefits, and that's what makes it it's a large claim, I think. I'm not making a value judgment here. I'm just saying this is the claim that the critical brain hypothesis scientists are making.
Yeah, I think it's valid to call it out. And I think part of it is that there's data that shows that waking brains seem to be near the critical point. And
Hmm.
so we have data that's suggestive of that. And so then
Yeah,
if
I'm
people are
not, yeah.
trying to like if people are trying to think of like why would this be? I think that led to the critical brain hypothesis, which is, oh, well, criticality offers these things, so it makes a lot of sense that, you know, we would have evolved this way, right? Because it's giving us all these things, and so that's why
Right.
currently we have this like
Right. So all
critical
these
brain.
these three functional benefits you have, like maximal dynamic range, maximal information transmission, representational capacity, these are folded into the story of survival, and so on and so forth.
Like, let me know if you want to go
Mhm.
back to these animal studies that I had pictures of a little bit earlier.
Okay,
Um,
maybe we could. Maybe we could. Is there anything with the visual cortex?
so what they did so I'll give you like high level, and like you let me know how many details you want.
Hmm.
Um, and so high level, what they did in this study is they took rats and they sewed one of the rat's eyes shut to monocularly deprive that eye, right? Because it's sewn shut. And
Hmm.
so in the rat, they did that to one eye, but not the other. And then what they did is they recorded from both visual cortices. And so as you're familiar with, brain anatomy, each eye goes to each visual cortex, or each visual field goes to each visual cortex. And so they recorded from the eye field to see what happened based on the control eye versus the deprived eye. And what we're looking at in these plots on the right is the most important ones are this plot here and the one on the very bottom, where on the y-axis we have a measure of criticality, where higher on the axis is less critical and lower is more critical. And on the x-axis we have time. And so what we can see is that when the eye was deprived, so at this blue arrow point here, we see almost an immediate jump in the criticality that they were measuring from the visual cortex of this rat. But interestingly, supporting this homeostatic idea about criticality is that over time, the jump in the deviation from criticality like reduced back down to the baseline levels that it was at before any deprivation occurred. Whereas no change in criticality occurred in the control eye at any point in time.
But but the going up means that it went less critical and then it came back to its baseline criticality. Is that correct? So
Yeah,
it was
so like it was
subcritical,
perturbed,
right?
like
Right.
yeah, yeah,
That's cool. Is this one of the things, because we're just looking at eyes at this point, right? And then this is the
yeah.
kind of thing that you can start talking about criticality as like not only scale invariant, but probably like anatomically scale invariant in that these different organs, and like when they're attached to some neuronal mechanism, will exhibit these kinds of criticality set point stuff. Is that, or is that too much?
Yeah, I think actually maybe a better conclusion to get from this slide is like, so we're only looking at the brain in this slide. Like,
Hmm.
we're manipulating it based on a sensory organ, which is the eye, but we're only measuring the activity of the brain.
Hmm.
Um, and maybe what's, in terms of the scale difference here, what we're doing in this study is that we're able to insert an electrode into the visual cortex. And this electrode is able to record action potentials from individual neurons. And as you're familiar, action potentials are like the signal neurons send to each other. Um, and these action potentials, like to be able to measure multiple neurons, it's really hard because they're individual cells, so they're very small. So to get good resolution of your individual cells, you can only measure a small area of the brain because we don't have tools to measure
Individual.
individual cells everywhere, right? So this study did like neuron specific recordings. And so they inserted this electrode and they were able to record across the whole length of the electrode multiple different neurons, but they only know what's happening to these neurons that are immediately able to signal onto this electrode. Um, so what this study is showing that within is that what this study is showing is that within the visual cortex, we can see this homeostatic criticality mechanism that was suggested by the earlier slide that I showed. But what this slide is not showing is like global criticality across the brain
Mm-hmm.
or global criticality across like the whole occipital cortex, which is the very back part of your brain where this recording site is. So it doesn't give us any indication about like whole brain criticality, rather like just visual cortex criticality.
Would it be crazy to imagine that there is some kind of compensation going on? So, okay, you've lost, so to make up for, I don't know. I'm assuming that globally you would also try to maintain a set point. But let's say here you have to do some kind of compensatory work to get it back to this critical region, but maybe globally now, or in some other aspect, you're bumped up. I don't know. Like there's some, what do you call it? Conservation of criticality across the board, I don't know.
Like you're saying like in this region here, like this time period here, we see this increase in criticality here, but are you asking like if global criticality is maintained, so somewhere else we're gonna see like an extra
Exactly.
dip in criticality?
Just an idea, just a
Yeah.
spurious thought.
No, I think that's a good hypothesis. As far as I know, it hasn't been seen. It hasn't been seen. It hasn't been, as far as I know, like rigorously tested. But we have two types of recording people do in the brain to test criticality. And there's this version, which we call like spike recording or like single neuron recording. Or this is called multi-electrode recording, which means we're getting multiple individual neurons, right? Um,
Mm.
but we can also do something like EEG, which is where we stick electrodes on like the surface of the scalp to try to measure like global dynamics across the cortex, which is a totally different scale from what's being done here. But when we measure global cortical dynamics, we have similar results.
Oh, oh.
Not specifically with this visual,
Mhm,
not
mhm.
specifically like visual cortex results, but like we can see like global brain criticality seems to be maintained in the awake state, but in like perturbed states like unconsciousness, like by anesthesia, we lose the global brain criticality.
Okay, cool. This is interesting, because the eyes are functional. They're just shut. It's just darkness. Is that correct?
Well, it depends how you do. Like one eye is operating as normal. the other eye is not getting any input. So you would argue probably that it's not functional because it's not providing visual input to the rat.
But it's like, is it really zero? Like, because I can close my eyes and still.
Yeah. As far as I know, they did not control for like, more like luminosity, like ambient
Mm-hmm.
light
Mm-hmm. Mm-hmm.
coming through like the closed lid of the rat. And they didn't like destroy any part of the optic
Okay.
tract. So
Okay.
they just closed the eye. But this was enough to cause this perturbation of criticality. So they got experimental results that they wanted or that they were interested in.
Yes.
But yeah, I'm not sure that they controlled to like they definitely didn't like damage the eye. They just closed it.
Yeah, but that's not the point of the experiment. Okay, got it. Got it. Okay, okay.
No, but that's good to clarify. Yeah. Yeah. Yeah, and so this other experiment I don't think is that interesting to go into. It's just they also found that the visual cortex has criticality with the same method where they did spike recording. And so we have this. And then if we are ready, we can talk about some applications of this to consciousness, which I think is cool. And so there's this, because this is what I do. And so there's this study here that came out last year that was really well done. It was a really beautiful result. And so I'm going to talk through this experiment. I have one other data slide on this topic, but I maybe won't go into detail in the second one. But this one I think is really worthwhile to go through. And so what happened in this experiment is they had 3 different groups of subjects. So like this one and this one and this one. And what they did with each subject group is they were human subjects and they recorded EEG, which recall we just mentioned is when you stick electrodes on the scalp of the people and you're trying to record the cortical activity of each person. So they had each person have an awake state where they are just sitting and they're resting, and they report that they're having conscious experiences during the awake state. And then the subjects are anesthetized with one of 3 anesthetics. And so this is either ketamine or propofol or xenon. And they anesthetized each subject to a depth where they were quite unresponsive. So they wouldn't respond even to a very strong stimulus.
Mm-hmm.
And then they let the subjects sit at this anesthetic dose for a while, and then they let the subjects recover. And then after the subjects recovered, they asked about the conscious experience of the subjects while they were under the anesthesia. So it's recalled consciousness at this point. Mm-hmm. And in the cases of xenon and propofol, the subjects did not report conscious experience, but under the ketamine anesthesia, the subjects did. Like subjects in this case had like these crazy, wild, like trippy dreams while they were under the ketamine anesthesia. And so what's interesting about this study is that the subjects who are awake, so the ones that are green here, all have low, all are highly critical. And so they all have high criticality in agreement with the data on previous slides showing that awake animals are near critical in their brains. What's really interesting is that this study showed that consciousness correlated with criticality more than just behavioral responsiveness, because all 4 of the states that are near the bottom here have reported consciousness, so including this ketamine anesthesia case, and all of them have indistinguishable levels of criticality, and this is different from the unconscious cases on the other anesthetics.
Interesting. So this is why you say higher order functions, and because you can have like stimulus responses that seem like behaviors or are behaviors, and yet that need not be a signal for consciousness. And yet recall is a better signal, and therefore you can, and given that in those cases you had this critical signature, you can tie criticality to consciousness. Is that a good kind of
Right. I think I would agree with definitely the track that you're on, which is that maybe rather that behavior is a bad indicator of consciousness.
Mm-hmm, mm-hmm.
Because in all three anesthetic cases, the subjects were not responsive, whereas they were in the three waking cases. And so I think this is a really good study that shows that responsiveness is not a good indicator for consciousness. You can think of if you're under anesthesia in the operating room and they're trying to check if you're out by like, poking you, right? Like, you might not respond to the poke, but you might still have conscious experience. And so this study is supporting the idea that there's more than just behavior that indicates conscious experience.
But what implicit in this is that things like memory, recall are tied to consciousness and like higher order functions, right? So that's kind of the behavior that we're looking for here. Is that
Right. Yeah, that's good. Right. That's a good point. Which is, yeah, so maybe you could even argue that a limitation of this study is that it required subjects to tell you that they had conscious experience and also that they remembered conscious experience to be able to be counted in this consciousness reporting group here.
right? I mean, so the worst, like the bad faith interpretation or something like that would just be like, okay, so the memory, there was a problem with memory. Like we can say nothing about consciousness. This is a memory issue. Like, would that be a fair or like, it's not nice to the researchers, but
No. I mean, I think it's actually important. Researchers should be rigorous, right? And yeah, I would say that is a limitation. Like, it's totally possible that the difference between these three anesthetics is that propofol and xenon destroy memory recall, whereas ketamine doesn't. But it's interesting, and so maybe that's what criticality is indicating, which sort of ties into this higher order functions idea, which is loosely represented here, right? Like, criticality helps give rise to these higher order functions like memory, which we can see here, but also this idea extends to higher order functions like, being able to have complex thoughts, right?
of course. That's very interesting. I think from like a robotics perspective, it's a bit of a leap, but it's quite easy to make robots that move and react to stimuli and stuff like that. And from that standpoint, it's and because of that, increasingly, it's like if you want to say something is intelligent, it's not good enough to say, okay, it walked around. Like at this point, you can train any neural network to do some kind of physical behavior, and this kind of falls in line with that kind of need for rigor in saying this is intelligent versus this is or like this has some self-awareness or whatever or higher order functionality. So yeah, I'm with it in general. It's just yeah.
No, I think that's important. And also, like, maybe a way to distinguish it too is like the complexity of the behavior, or maybe the right. Like, I mean, I suppose you could argue depending, because intelligence, right, is one of these squishy words, which it's like hard to define, or everyone defines intelligence differently, right? And so someone could argue like, well, actually, like, I might call a robot that can walk around intelligent because it's able to have this like control over its limbs. And then maybe we would say, oh, well, but it doesn't count because we programmed it to do that. And so it's not actually intelligent because there's like no thinking going on. It's just following this like, simple couple lines of code here, right? So I think it's, maybe we could talk about it in terms of like degrees.
Sure, degrees, but the real point I was trying to make here was like this response to stimuli, which is easily observable in behavior, even in
Yeah.
robotics increasingly, is not a sufficient marker for what you would call higher order capabilities. And I think this kind of falls in line with that idea here that you can imagine human beings having reflexes, having these easily identifiable markers, but criticality, like assuming that their story, this is the story that we're going with, is a better marker, right? So yeah, I mean,
Right.
I'm just trying to make a bridge here, and I think there's something.
Yeah, and actually, I'm glad you said this because it, helped recall like an advantage of this is if there's enough evidence that criticality is evidence for consciousness or evidence for intelligence, right? Like criticality can be measured from the network without any behavior.
Right.
And
Which is a
so,
strong suit, which is a strong point. Yeah, yeah. Yeah.
right, right. And so if there's enough support for criticality as an indicator of X, right? Like then we wouldn't need we wouldn't need another measure.
Behavior.
Like for example, in humans, right? Like if you've got somebody in a coma,
Hmm.
right? And we're pretty confident that criticality is an indicator of consciousness. We could put an EEG cap on this person in a coma and measure. And
Right.
if we see that they're critical, then that might lead us to conclude that, oh, this person still is conscious, like they're still in there. They just can't do anything to show us that that's true.
Right. And then that has like social implications. Yeah, absolutely. Yeah.
Yeah.
Okay.
Yeah. Um, right. But to make that conclusion, there needs to be, like, this is one study. So there should be, like, lots of studies that support that idea, right? To fall on that conclusion.
Hmm.
Right. And so I have, this is a graph that we don't need to get into, but it's, with a different measure of criticality is also seeing that in humans, this conscious state, this CS state is more critical than these perturbed states. And this study didn't do much with consciousness, but it's just an example in humans of this wakeful state being near critical.
And the sort of ideal, so we have supercritical, subcritical, and if I recall correctly, you want to be a little towards what? Was it subcritical? You want to be a little
Yeah,
subcritical?
so if we recall from this graph here, most studies in animals find that the brain is just slightly subcritical. And the reason for this, so the theoretical idea is that perfect criticality is like gets the most advantages. But the realistic implication of this is that since we're animals that take inputs to our system all the time, to be able to deal with this, the brain settled on this point that's just below criticality. So it's getting most of the advantages of the critical state, but these inputs to the system aren't pushing it into a highly supercritical state, which, would be detrimental to the system. Like
I
it's
see.
preventing like runaway growth, right?
Okay, it's better to be on the safe side. Yeah. Okay.
Yeah.
Okay. Okay. Okay.
Right. And so I have a couple slides on some artificial intelligence application of criticality. And the first experiment that I am showing is sort of bridging like AI and neuroscience. And so if you haven't seen this before, it's super cool. What the researchers did is they took a cortical sheet of neurons. So they took neurons and they put them on like a plate. But the plate they put the neurons on was like a sheet of electrodes. And what they did with this sheet of electrodes is if neurons were in like one area of the electrode sheet, their activity was recorded as output of the system that was used to control this Pong lever. And if you're not familiar with the video game Pong, it's where you have to move a lever up and down to keep the ball that's going across the screen from falling off the page behind where your paddle is.
Oh, is that what Pong is? Okay. Okay.
Yeah. And so you can play Pong with like two players where each player has one paddle on either side of the screen and they're trying to get the
No,
other
I was
player to miss.
joking. Yeah.
Yeah. Um, yeah, and so it's super cool. So they had one side of the electrode dish like controlled the Pong paddle, and the other side got input from the video game space to talk like to give information to the cortical sheet, like where the ball is and where the paddle is and like what the state of the game is. And they did like some reward learning with the cortical sheet. It's like if it missed the ball and like lost the game, it like got a negative stimulus. Right. So I thought this was insane when I saw it for the first time. I thought this was crazy. And so, interestingly, this paper also links this idea to criticality. And what they found in this paper was that when the cortical sheet, like looking at the activity of the cortical sheet or the neurons in a dish, they found that while the sheet was performing the task, it was highly critical. But while the sheet was resting, like not doing anything, then it was in a more subcritical dynamic. And so they quantified this in a couple of different plots. And so We can see this in the two bar plots, which are two different types of criticality measures. And we can see that in both cases, when the sheet is in gameplay, it's more critical than it is when the sheet's just at rest. And we can also see that they found that when the sheet was more critical and also performing the task, it had better performance the more critical the system was.
Wait, what does
So
DCC stand for again? I know what branching
it's
is.
yeah. I'm glad you asked. So DCC stands for the deviation from criticality coefficient. And so what that means, right, is zero deviation means perfectly critical, whereas a bigger number means it's more and more deviated from the critical state.
Okay.
An HM ratio is a measure of performance. It's the hit-miss ratio. So the bigger the ratio is, the more hits there were relative to the number of misses. And so we can see this, this loosely negative relationship where lower DCC values, which means again more critical values, correlated with higher performance on the.
Wait, give me a sec. So
Yeah.
you want the HM ratio to be what, higher, because then you're winning more. And as you go right, you go lower, so you're more critical. Okay. And
Or if you go as you go down, you're more critical, and as you go right, you have higher performance.
right.
Yeah.
And the thing here is, in these, we generally, at this point, we don't even talk about critical regions. It's almost like the plot is just critical to, right? We're only looking at one half of that kind of graph that we have. Is that normal? We kind of throw that part away, the supercritical.
Yeah. So I think with specifically the DCC, which is this measure, the deviation from criticality coefficient, DCC does not measure directionality at all. And so it'll tell you how close to criticality you are, but it doesn't but when you're deviated, you don't know if it's towards subcriticality or towards supercriticality.
Mm-hmm. Mm-hmm.
But you do know that with the branching ratio. Because recall from very early in the presentation, the branching ratio, which was sigma in that guessing game we played, when sigma equals 1, which means the critical state here, when sigma is 1, we have like 1-to-1 fidelity of information transmission. So as we're going through, like an activated node is likely on average to activate one other downstream node in the next time step.
Yes.
But when the branching ratio is less than 1, that means that we're decaying. So, on average, less than 1 downstream node is activated. So we're going to lose, our signal is going to die out as we go on.
And that's
and so
you can use the branching ratio to get a sense of the directionality instead of just
right.
the pure, what do you call it? Yeah, okay. Deviation.
Right.
Yeah.
Right. Okay. And so this is an indicator, like on the previous slide we saw that they said at rest is more subcritical, and these branching ratio results support that because they're less than 1. I think it's worth mentioning that a reason you'd want, I mentioned earlier in the talk, you definitely want to use more than one measure to identify the criticality of your network. So while the branching ratio gives directionality, you want something else to corroborate your results. And the DCC is a new-ish measure for neural data. It's getting a lot of support because it's supposed to be more rigorous than other measures of criticality. Because within its calculation, it's asserting that multiple things must be true for DCC to be near 0. So it's sort of comparing multiple things at the same time to give you your one number output.
Okay. Okay.
All right. Yeah. So I just said, I think this is also important to note where I just gave DCC really high praise because it's a more rigorous measure of criticality because it's accounting for multiple variables. But I think it's important to mention that there's several limitations to DCC, which is that to use the measure in the first place, you need to set like 4 or 5 different parameters so that you're sort of filtering your data before you get to the step where you can even evaluate DCC. So there's maybe more subjectivity involved with DCC. And also you're within like a much broader parameter space when you're trying to evaluate this metric. So it's really important to do it with really strong precision and also to identify like the caveats of the measure.
Seems like there's just looking at these plots, a lot of variance in the rest, and the gameplay is like
Hmm.
tight, super tight, which says something. I don't know. It feels like I don't know, attentional focus, or you know, you gotta lock in. You know.
Yeah, I mean, also, like, I don't know, when you take, like, basic stats, you're taught if you're gonna do a linear fit to your scatter plot, you should first check to see if it seems like a linear fit is appropriate, right? And I think your observation that there's high variability in the data is good. And so, if we're just thinking like our statistician's self, if we take away the red line, I think it's sort of hard to see this trend that the linear fit picks up on. Like it looks a lot more similar to maybe a cloud of data points than
Hmm.
it does to a linear trend, right?
Yeah, but I was pointing more to the rest state being like the box plot
Oh,
being
and the
quite big,
box plot.
and
Yeah,
saying that
that's also, yeah.
when you're locked, it's
Yeah.
almost like when you're doing the task, I don't know, you regulate towards a much smaller space, almost like you're locked in. Whereas resting, you're more
Yeah.
like, I don't know.
More free to do different things. Or like
Yeah,
you have
I know that.
more.
Yeah, not to
Yeah, that's a great
anthropomorphize too much.
observation.
Yeah.
Yeah, I mean, I think like even if we think back to, oh, I guess we didn't really go over the slide, but I suppose if someone went back and paused the video, the second rat study that I showed also has really high variability between the two states.
Hmm.
Um, just like we can see here, like even in the rest state, like the upper whisker of the box is even more critical, like at the most extreme value
Hmm.
than the most extreme value of the gameplay box.
Hmm. That is something. In the rest state, are things being updated? Are they learning stuff? They must be learning stuff from when they did gameplay, right?
I haven't read the methods in enough detail, but I guess I get the impression from the rest state it means that they're not like
They're
I
not
think
being
what happens in the
rewarded.
rest state,
Yeah.
they can't move the Pong paddle, like the output layer is shut off, and I think probably also the input layer is shut off. So it's just like the neurons in the dish, like behave however they want, but they're not getting any
Right, they're not
reward
coupled.
or punishment signal. I don't think
Right,
so.
right.
Yeah.
They're just like decoupled from the. But I think that, I mean, it's just spurious ideas here again. But if you could imagine this is kind of like sleeping, and then you've played the game, and the fact that you do find instances of criticality beyond what you would have in the gameplay. But it's almost like maybe you can afford to do that, because you're not coupled to the environment, so you have less risk of this runaway plasticity damaging you or something. So you can like do stuff like make updates and change your parameters. I don't know what these neurons are doing, but might be something. I don't know. Yeah.
I mean, I think that's a good thought because like let's just go look at this rat study. It's relevant. It's become relevant. So we check out this rat study. What they did in this rat study is they again recorded from the visual cortex of the rat with the electrode array, but they only recorded one visual cortex. And they did this chronically over several days. And so what they did is they recorded the brain activity and then they segmented it into little chunks to give you each of these data points in the graph we have here on the left. Um, and so then they also labeled the like little chunk as being in the wake state or being in the sleep state.
Mm.
Um, and what they found is that the sleep state was more critical on average than the waking state.
Mm.
Um, And so, following along with the idea you just had when we're thinking about the neurons in a dish with the Pong game, maybe now that the animal is asleep, there's fewer inputs to the system, so it's able to operate down more at a more critical state and, engage in some of these functions that we think like sleep is good for, like maybe some memory consolidation or like processing of information, which is less able to do in the awake state because of this buffer we have towards slightly subcritical
Yeah.
in normal dynamics.
Yeah. Yeah, just like, spurious thoughts. Like that almost like kind of ties into almost like kind of metacognition going on where it's like now that I'm not coupled to the environment, or now that I sense less of a risk of this becoming runaway, I can attempt, like to get closer to these regions that are a bit more dangerous without the possibility of it becoming super critical. And if like criticality and stuff is a measure of these updates and these changes and plasticity and so on and so forth, then that's interesting for like learning consolidation, given that you've had this awakefulness period. Yeah.
Right. 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 Yeah. I think that's interesting. Right. Yeah, there's more parallels between this study and the
Yeah.
and the dish study.
Yeah, yeah, yeah. Actually,
That's,
but it's really cool that you line these three up. I think they're really good. You know, actually, we probably needn't have skipped this one that quickly. And in fact, this kind of opens me up. This kind of sleep wake thing and criticality. Now that we're talking about it like this, opens me up to the depth of it, because it's not just, oh, you can find criticality signatures, and then you're looking for the awake state, and then it's like, oh, let's not worry too much about. Now you can start thinking about the dynamics of it, like, okay, you're coupled to environment more versus less. What does that mean for criticality? And maybe a lot of the issue that you saw with the results contradicting each other could be reconciled from this more holistic standpoint. You know?
yeah. Yeah, and I think these results show just like the high variability there is within different states.
Mm-hmm.
Because we saw in the neurons in a dish study and also in this study here where there's lots of overlap between the two
Mm-hmm.
different
Mm-hmm.
groups. It's just that, on average there's a difference, and so we see it statistically that there's a difference. But if you just took one sample randomly, it's not as cut and dry as you might be led to believe. You might be led to believe with, like that bell curve that I showed on an earlier plot that's showing how like different altered states are, so and so far different from the
Yeah.
critical state.
Yeah. Yeah.
Yeah. And then on that same topic, like this follow-up slide might be interesting to you, which is from the same study. It's just showing across a what is that, 3 hour period? What is that? 3 day period? 0 to 120. Hold on. I can't do math. 4 to 5 to 7 to 6 multiple days. Jesus.
Yeah.
That many days. Period. That many hours. And so what you see in the dots is each dot is a recording that it's a unit of time that they grouped into a single DCC measure. And then the dark and light is telling you like if the rat is in its dark phase or in its light phase.
Mm-hmm.
And something that is important to know if you're not an animal researcher is that rodents are active during the dark cycle and they sleep during the light cycle. So it's flipped from what humans do.
Wait, does that
And
mean they're
so,
nocturnal? Does that mean dark cycle means what?
yeah, nocturnal.
Okay.
Yeah. And so if you're in a standard animal lab, you force the rodents to be on sort of your, like, when you do animal studies, like they're the lights on when you want to do your experiments, so people have to navigate around how to deal with that. Like either they need to like make sure their animals like woken up before they do their experiment, or they're gonna deal with a partially sleepy rodent, or they switch the light cycle of the rodent so that their rodent's natural state matches up with the human's natural state.
Oh yeah, rodent jet lag. Yeah, tell me
Yeah,
about.
yeah, yeah, yeah.
Yeah.
Um, And so that's not necessarily relevant to understanding this. It's just like a fun fact. Anyway, so what they did is they recorded from these rats like longitudinally over time, obviously, and then they took like just to show a little bit more specifically what we're looking at here. They took a subset of the data, like this red box, and they broke it out over here, where we can see the differences between the active wake state, where the rat's like moving around doing stuff, the quiet awake state, where the rat is like sitting and resting, like not doing anything, versus the NREM sleep, which is like slower wave sleep, and the REM sleep, which is traditionally thought of as dreaming sleep in humans. It's more active sleep, but you can also get dreams in both states in humans, both types of sleep. Anyways, and so it's interesting here to look at this and sort of see more in real time, like the variability there is between these different.
Yeah. What is it? So this red block takes out. So this purple in the middle is analogous to that switch between light and dark, right? The quiet. Is that no?
Hold on, I have a blue light filter on, and so I can't see the colors actually very well, so let me go turn that off, and then I can, okay. So if we look at this red, so this red state, the rat is awake, but they're like resting, like if you like sit on your couch and you sort of stare off into space, like that's kind of like quiet resting in humans.
Oh no, okay, I see. No, you can turn the blue light filter. I get it. Okay, the whole thing,
Okay.
because the time. Yeah. Okay. Yeah. It's
Yeah,
120.
yeah. So the whole time it's red. That's what this like decoder they had. Actually, I forget how they marked it. It either was with a decoder or a human sat and like looked at every single time point and like marked like which of the four categories it fell into.
And okay, so we have active, quiet, and REM. And how does this tie into restoring critical brain dynamics?
It doesn't necessarily. It's just showing you how the DCC, which again is this measure of criticality, is changing over time and how it's highly variable. So
Your
we
slide title
saw.
literally said restore critical brain dynamics.
I just kept the same title from the previous slide. Sorry, I didn't think about it.
Okay.
Yeah, right. So yeah,
Sorry.
this is all from the same figure. Actually, I just broke it into little pieces.
Okay.
Like
All
it's
right.
like
Okay.
panel
I
like
thought it
A
was a
through
different
D is
study.
these slide. Yeah.
Okay.
Um,
Okay.
but it's sort of showing the same thing. Like this graph here is a summary graph where if we look at all of the sleep states versus all of the wake states, here's the difference we get. Um,
Mhm.
and then this illustration is I think from one rat, and it's showing you how variable the DCC is across time. And then this subgraph is sort of showing you across states, like sort of what the behavior
Mm.
is. But there's a few things that we can see from this graph that are interesting. They also had this in a summary graph in a different part of the page. So if you're interested, you can go look up the paper. I didn't include it in the presentation. But what you can see here is if we look in an active state, so like this green or this green here, we can see that across time, it seems as though we start from a more critical state, which is like lower down the y-axis. And then across time, as the time goes on, we decrease our criticality progressively. We're losing criticality the longer we stay awake. We can see that also in this other large active state where we start from highly critical and we decrease away from the critical point as the time goes on up the y-axis. And so what sort of the authors concluded from these findings is that maybe the reason that the sleep state is closer to criticality is because during the wake state we progressively get less and less critical. And so the sleep state exists as like a hard reset where we're gonna like restore the criticality we lost during our regular day.
Interesting. I This is another spurious thought that I had was that the causal story here is that sleep is a mechanism for active behavior, and that's why it's like this restorative force. But what if we flip it and then we're doing activities so that we can sleep good? Like the point is sleep. Like really, we want to be in this dream world, but we can't. So we have to go out and do stuff. And then, you know what I'm saying? And then you're like, okay, good work. Because many people
Like
love sleep.
rewards.
Yeah, it's like a
Yeah.
reward for being able to dream.
Yeah.
That's kind of like the office is like who wants to go to the office, but then you get to go back home and do whatever you want.
Yeah.
So
Yeah. Yeah.
yeah.
Actually, when I first read this paper, I was like, what the heck? Like, why wouldn't animals just always be asleep if that's the state that seems to be this restorative function? Like, why wouldn't we just always sleep? And then I was like, well, obviously, because, we have to go eat food, right? Like, we have to run
Right.
away from predators. We have to, you know, manage living in a non-static world, right?
Sure, but then that becomes also it's like, but you do that for what reason? To sleep. It's a cyclical thing where like the causal story can go any way you want. You don't
Get it
have to
going.
assume. Yeah, yeah. You don't have to assume
Yeah.
that.
Yeah. Yeah. Yeah, good thoughts. Good thoughts. All right. So these we covered all the animal studies, and then we covered the neurons in a dish playing Pong study. And so I have one more study that's related to artificial intelligence that I thought might be interesting to talk about. And so this slide obviously has a lot of information on it. So we'll try to go through it slowly so that we can sort of follow along with what they did in this task. And what we're going to see is that large language models that were trained on more complex data demonstrate more intelligent behavior. Intelligence here being measured by performance on the downstream tasks. And so what they did in this study is they took elementary cellular automata data to pre-train a set of 4 different large language models. And as we're familiar, elementary cellular automata are these one-dimensional systems that follow a set of ECA rules. And what we do is we start the system, the one-dimensional system, at time 1, which is the top row of like this example plot here at t equals 0. And then we choose one of the 256 rules that are possible to follow for until time t. And so at time t equals 1, we follow the rule and it's going to cause a specific change in the system state. And then if we just let the system run until time t, we can like look back across time to see like the picture to see what it looked like as the system changed state. And so these rules, they fall into 4 different classes. One of them is the uniform class where the system is going to pretty much do the same thing across time. Once it hits like a certain threshold, it's going to be the same. The periodic class where it's sort of the system will sort of cycle between a couple of different states as time goes on, and the chaotic phase where if you measure with chaoticity measures, we get that kind of dynamics over time, versus the complex class which exhibits complex behavior across time.
Does a complex one give you scale invariance, or is that not relevant to this?
Yeah, that's a great question. So the reason that I included this here with the criticality talk is because complexity correlates very strongly with criticality. And so I thought this was more cut and dry than it sounds like it actually is. Like the cut and dry version is that complexity is maximized in systems when they're at the critical point. But I, was doing a little bit of like extra research for this talk to make sure I didn't totally say anything off base. And it sounds like, in fact, this rule with complexity peaking at criticality is actually more nuanced and maybe not like 100% true. Like complexity should be high for sure near the critical point, but it's not necessarily maximized exactly at the critical point. So this study is interesting because it definitely points to hypotheses that will relate to criticality, but it's not measuring criticality in this study.
Okay. Thank you.
Yeah. I'm glad you asked. I meant to say it when I started and I forgot.
Oh yeah, okay, cool.
So anyways, so what they did in this study is they broke these ECA rules up into 4 groups, and then they used data from each of the 4 groups to train 4 different LLMs, or pre-train 4 different LLMs. So we've got like the uniform, the periodic, the chaotic, and the complex large language model. And then what we did, or what the authors did, not us, is they now post-train, they post-trained the large language models to perform these downstream tasks. And so there were 3 options. There was 2 versions of this Tetris task, and there was a chess move prediction task. And this is not actual data. It's more of a schematic representation of data we'll see in the next slide. But they saw in general that with increased performance occurred when the large language model was trained on more complex data. And they saw this with multiple different measures of complexity. And so I think I have a slide on ECAs. I do. So we talked about it already in the past slide, but if you want to look at a whole slide, you can pause the video here. And then now we can look at some actual data from the study. And so, so we've got 3 different columns. In column 1, we're looking at the easy version of the Tetris task. In column 2, we're doing the hard version of the Tetris task. And in column 3, we're doing the chess move prediction task. And so on the top row, we're using the complexity measure Lempel-Ziv. And on the bottom row, we're using the Wolfram class complexity. And then on the y-axis, in these 2 columns, we're looking at efficiency. And in the 3rd column, we're looking at accuracy of the large language model. And so for the Wolfram class complexity measure, in all 3 cases, we have a pretty clear relationship of higher complexity corresponds with higher performance on the 3 different measures. We've got efficiency and accuracy are our 2 measures. And so this is maximized with the most complexly trained large language model. When we look at the top row, which is Lempel-Ziv complexity, we see a clear relationship in the easy Tetris task and pretty much clear in the hard Tetris task plots. But I would argue in the chess move prediction task, it looks more like a random data cloud. But the authors found a significant correlation with R equals 0.44, which is a moderately positive correlation.
Okay. For this one, I'm assuming, and the reason that you gave the caveat and you're being very careful with criticality and complexity was to not overstate anything. But if you were to be very rough, and if I were to try to interpret this, what you're saying is that the functional benefits that criticality give you can be related back to this notion of complexity in the cellular automata, that the Wolfram stuff. And therefore, this is another sort of nod towards why criticality is good. Is that roughly okay?
Yeah, I think that's good. That's a reasonable conclusion. Yeah.
Well, of course, the complexities of LLMs and what pre-training really means and what training really means is its own. But roughly, if this is something that you could do, what does pre-training have? What does it do? What is priming it for what?
Yeah, so what happened in this study is they pre-trained, right? And in the pre-training, they would give in they're training it on the whole matrix here, but they're using row 0 to predict row 1 and then row 2 and then so on until row T.
Mm-hmm.
So it's sort of next move, next token prediction here is what they pre-trained on. And then once the model got good enough at this, then it was counted as successfully pre-trained. And so to answer your question, the differences between these 4 networks is sort of their baseline dynamic properties.
Right. Okay. So however the weights are set up based on the complexity of what they had to go through before, and then now we train it on the downstream tasks.
Yeah.
But would it be crazy for someone to be well, yeah, you gave it a harder task? Because I'm assuming moving from left to right, it's more difficult. Is that fair or no? It feels like it's more difficult to do the complex. Well, chaotic feels like the most difficult one, huh? chaotic is like impossible.
Yeah. Yeah, I think it's interesting because all of the cases are deterministic because they're all following one of these rules, right?
Mm.
Um, but yeah, I,
But
I
deterministic
mean,
and predictable are different, right? And
yeah, right,
that's where the kind of
right.
the benefits of complexity as opposed to chaos comes in, I'm assuming. Because if it's chaotic, if chaotic means what it hints at here, it's like you don't get order at all. But if it's complexity, then maybe there's something similar to this invariance idea, so you can help with prediction, and that does tie back into being able to do stuff when you're given tasks. This is me being spurious. I don't know. Maybe I need to read the paper, but you know.
No, I think it's good. I mean, I personally still struggle a little bit with the specific difference between chaotic versus complex systems.
Mm. Mm-hmm.
But sort of what I've come to understand is that in a chaotic system, each of the nodes is like sort of independent, or it's following like very simple rules. It's not really like there's not a lot of interaction between the nodes.
Mm-hmm. Mm-hmm.
Um, like you can still it's still deterministic, but it's not there's not so much going on. Whereas in the complex case, there's a lot more.
Like global local interaction type stuff going on. Huh?
Yeah, yeah, yeah. It's a yeah, like more complex interaction.
Yeah.
Right, and so, but I mean, I think you're getting at a good question, which is like, okay, like why does it matter? Like, isn't it sort of like a
Self-evident.
self-fulfilling hypothesis? If we just trained on more complex data, like, shouldn't we get? But I mean, I think, I mean, okay, so you're actually probably more an expert in the AI field than I am. I mean, I'm not an expert, right? But like, from my understanding, right, like it's interesting, I think, that this study
No.
found that I think it's interesting that this study found that if you start with a network that had a different history than some other network, then with the same subsequent impacts on the network, then, some of them do better at learning this new task than others do.
Right. Right. Well, in my mind, and this is like once again, this is just my me thinking out loud. The interesting relationship is probably between chaotic versus complex, and it's kind of cool that you get the smaller variance, but because like again, we have to really look into what chaos and complex means within cellular automata language or a land. But if it is that you get this, it's sufficiently rich, and yet there are these rules, not in terms of the deterministic rules which generated them, but rules that can be inferred that help you with prediction, like some structural properties that can be abstracted by the LLM. And then that kind of pre-training helps with solving tasks in the real world. So that story feels good to me, and it makes
Yeah.
sense. And then tying that back into criticality, which posits this same thing where you have this global local thing, you have an invariance across scales, which I'm assuming these complex systems also kind of have. Based on what I saw, you get these triangular things, and they have the scale invariance thing going on too. So I see the story. I see why it makes sense to bring it up. Yeah.
Yeah. Yeah. Yeah, I like this study. And I also, as a neuroscientist who has a background in cognitive science, I
Hmm.
really thought at least as a conceptual idea this is really cool because, it's been shown, for example, like in like psychology studies that if you're a teacher and you're teaching your class, if you treat some students as if they're special, like you randomly choose your group of students and you pick your randomly chosen group of students to be treated as the special elite group, then at the end of the year, regardless of the baseline ability of the students who were treated as special do better on like, standardized tests.
Mm.
than the other students. And so, like, I don't know, I couldn't help but being reminded of these studies from uh, this study that we're looking at here, even though it's totally different. It's like, it's sort of like, look, like if you, like if you take the LLM, which have all the same like intrinsic properties at like baseline, then you give like certain types of treatment to the different LLMs, we then can see like predictably that on like downstream things that these LLMs are going to encounter like later in their life, so to speak, right? Life is
Yeah.
quite a
Yeah, I hear
biological
you.
term, right? But like downstream in their history, like downstream in their future. I mean, you get different ability to handle you know these different tasks.
Yes. Yeah, yeah. I like your parallel. I don't know how mechanistic it is, but it's a nice
Yeah,
parallel.
yeah,
With
yeah.
the
It's I
kids,
don't know.
with the kids, I mean, I thought, okay, that's cool that it doesn't really matter about their actual academic abilities, and that
Yeah.
this favoritism just skews stuff in a positive direction. I would imagine that what it does is it messes with the kids' self-perception, and having to handle that self-perception forces them to probably, I don't know, work harder, because now teacher thinks I'm smart, so I'm probably smart, so I have to get good grades, and you end up with that self-fulfilling prophecy
Yeah.
kind of running out. So maybe
Yeah.
it's kind of like I'm given complex tasks, I must solve them, and then when you get the actual real world game, you do better. So I can kind of see it. Yeah.
Yeah. Well, I this was awesome. So that this is the last slide that I have. I just have my thank you slide to my lab at Michigan here.
Thank you.
I'm happy to talk more about anything that came up during the presentation or something else that comes to mind. Huh? Of course.
I feel like I asked a lot of questions through it, so there are not that many with regards to the slides. I think it was great. Your explanations were so good. So thank you, and your
Awesome.
slides are very clean. So yeah, and you like handheld along the way, just the amount of handholding we needed. So I know we're probably kind of tired too, so I won't be too long. One thing that
Oh yeah, I can put
I
them back up, the slides, if you want them.
no, 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 it's okay. I want to show something. Oh, so one thing that I came to mind was, can you see this?
Yeah, I can.
So very mechanistically, there's this, I think, control engineer professor, Sepultre, and he had this. I went down kind of a electrical engineering rabbit hole, and they're positing sort of like scale invariant control mechanism, and he puts forward, which might sound, somewhat obvious, but positive and negative feedback control, which I really like. So you get, in a rigorous electrical engineering sense, the combination of both aspects. And I kind of see criticality roughly in that light. So this is just something that came to mind again in hearing you talk. So he has these kind of two dynamics, fast and slow. And then, they have the graphs. And of course, you have excitation and inhibition going on. So
Mm-hmm.
if anything, just to nudge my own memory about this. And then, of course, he talks about control theory, that feedback shapes sensitivity, how to extend this principle from a monoscale feedback controller to multi-scale network control architectures remains a puzzle. And then he puts forward that nodal control regulates both excitability and ultra stability by the combination of positive and negative feedback control. So really, like, and then this control principle is flexible, robust, tractable, provided that the actuation of each conductance is localized in proper amplitude, temporal, and spatial ranges. So this is a kind of thing that I think would motivate continued work in things like criticality, because that there are people out there that are looking at these things rigorously in like electrical control engineering fields as well.
Yeah.
I don't know if that jogs any thoughts, but yeah.
Yeah, in that paper you
Hmm.
just showed, are they talking about criticality much? I saw like inhibition excitation loops, but I didn't see references to like a
No,
criticality
no
type
references to
measure.
criticality at all. But
But you
they're
can build
talking
a
about
network, is what you're saying.
right, and
Yeah.
you can build networks of networks, right? And they're
Yeah.
talking about these in time and these phases and so on. So I mean to say that these things can be mechanized, probably.
Yeah.
They're at least they've been formalized and they've been considered as these scale invariant properties for control. So, and he's talking about like GABA
And you're thinking about like implementing this into like
type stuff, right? But what I mean is like these ideas are, and this is not that long ago. This is somewhat recent, but we're talking about like cells and like he's going, quite biological here.
yeah, I mean, all the words I've been seeing, I mean, at least on those figures you just showed are very
Hmm.
neuroscience-y.
Yeah, they are. So that's one
Yeah,
thing I thought.
like GABA is. Sorry, go ahead.
No, that's it. Go ahead.
No, no, I was just to say like like GABA is on that slide you just showed or that figure you just showed. GABA is like the inhibitory neurotransmitter. So like when neurons release GABA, they're inhibiting downstream cells from
Hmm.
activating.
Hmm.
And AMPA is the like an excitatory um, receptor. So like if you send the excitatory neurotransmitter out, which is glutamate, then it'll bind to AMPA receptors. Is one of them they'll bind to. It'll bind to AMPA receptors, and it causes an increased likelihood that the downstream cell will fire, will have activity.
I see. I see. Yeah. So there's like vague parallels even in super mechanistic thinking, I think, and the fact that they're
Yeah.
thinking like that broadly, I think is a nod to this kind of work. Another thing I thought about potentially was if we could extend criticality into like the social domain. So we're talking about like social co-regulation of criticality, just as we had sort of in the you sutured the rat's eyes, you can kind of get this renegotiation. I would imagine that just like sleep can regulate criticality. Why can't your friends regulate your criticality? Is all I'm saying. You know? Um,
Yeah. Little like positive negative reward, little Pavlovian
yeah, or
conditioning
yeah,
going.
somebody's like having a seizure and like you're probably gonna go and try to comfort them.
Yeah.
You're gonna like touch them and try to soothe them. That's
Right.
like a crazy example, but like that, but like many degrees separated from that to much more, you know, your day-to-day interactions. Just
Yeah.
another problem.
I mean, on a totally different scale, I wonder how well we could think about like criticality of social networks, right?
Yeah,
Like not within brain, like but within like person to person
yeah,
interactions.
right,
Criticality,
right.
right?
And given it's well, so that's kind of what my master's work to some extent is about. I don't necessarily use criticality, but I'm looking at like agent-based models and looking
Yeah,
so you
right.
can do that.
Yeah.
And of course, because neurons are societies, right? So it's just moving the formalism over.
Yeah. Yeah.
Another thought I had was about, well, close with something more personal, but so we talk about edge of chaos, and I thought about the reverse of this would be the edge of control. And would it be fair to say criticality lives at both? Or,
Yeah, when you say edge of control, are you thinking of something specific or just like the same thing as edge of chaos, you just are using the opposite?
yeah,
Like
because
I would imagine. Oh no, go ahead.
yeah, because this is me trying to, just like I did with the sleep thing, trying to
Yeah.
like flip it and see if the causal argument still works the other way and see if there's anything to be gained in just attempting that mental exercise. And when I think about like homeostatic systems in general and the need to learn plasticity, edge of chaos has been used in like A life stuff to think about like how you can get dynamic switching, how you can like get these limit cycles, how you can get itinerancy, and so on and so forth. And the metaphor has been, oh, you want to be on the edge of chaos. But also, you can imagine like an excessively homeostatic system being completely incapable of doing anything unless it's perturbed by the environment. And that would require that, okay, if you want to be like an active agent in the world, you're doing some kind of self-perturbation, you're challenging yourself in such a way that you're also attempting to be on the edge of control, where you're not completely able to regulate everything, right? But you're on
Yeah.
that edge, you know?
Yeah. No, I think that's a good point to bring up, but I think maybe for two reasons. And so like with specifically phrasing it edge of control, I would think edge of control and edge of chaos are the same thing. Because if your two states are super controlled versus super chaotic, like the edge is the same thing, just like which way are you gonna fall.
Mm-hmm.
But to answer, the question you're getting at, which is like, well, aren't there multiple, state transitions happening, and like how do we manage the multiple state transitions? Like in the brain we have chaos and control. We also have like excitability and inhibition in the brain. There's another one I forgot, like off the top of my head, but there's these different
Upregulate, downregulate? No, I don't know.
yeah,
That's kind of
but
acceptably too, yes. No, okay.
yeah. That's not what there was this paper I read. I think it's called "How Critical is Brain Criticality" or "How Critical is Criticality," something like this.
Oh, they already did it. They already did it. Is there another one called A Critical Review of Criticality? I bet somebody's done.
Haven't seen it yet. You could be the first. Um, uh, no, but anyway, so this paper though, if it wasn't this paper, there's a different one that exists that talks about these three different example phase transitions, and sort of what I got out of it. I'm still sort of thinking through it, and it was that, in the waking state, we should be at the phase transition in all of the phase transition possibilities. Like we should be at the critical point of all of the critical points, right? Like we should be. It shouldn't be like I'm phrasing it poorly, but like we should be at all critical points is maybe what I'm trying to say.
What?
Like
In the
in the waking state, if the hypothesis is that we operate at criticality, just saying that is ambiguous. And so what the conclusion that I got from this paper is, meaning every critical state, like, if we're going to look at chaos versus order, we're at that critical point. If we're looking synchrony versus asynchrony, we're at that critical point, right? If we're looking excitation versus inhibition, we're at that critical point. That's probably the other way, synchrony versus asynchrony.
Integration
so we're at all
versus differentiation. Yeah.
Yeah.
Yin versus yang. No.
Right. So so it gets sort of out of hand with criticality. It's like, well, there's so many, there's a bazillion like things we can oppose as phases, right? So sort of what I got out of that paper was that we should be at all of the critical points. But I remember leaving feeling maybe mildly confused about it's like, well, how, like what does that mean? And so if we're trying to analyze whether or not the waking brain is at the critical point, like we're gonna pick a couple of measures, and so but each measure is only measuring one type of phase transition, like it's only measuring chaos versus order, or it's only measuring synchrony versus asynchrony, right? Like how, so and so if we see like, okay, in these ones we know of, we're at that critical point, like, well, what if there's some other phase opposition or like some other state opposition happening and we just missed that one? So like now is that like we didn't do an exhaustive enough search to be able to conclude that the brain is critical? Or like how can we interpret the different types of critical points? Like what does this mean? I haven't found a good answer to that question.
But that question makes me almost feel like it's the honest question, and I could be wrong here, this is my Spears thinking again, but I think it hints at the real motivation, which is just this general intuition that there's these oppositional phases, and almost like kind of playing with paradox, and we should just line all of them up. It makes sense. So I don't know. Yeah, that kind of brings me into the kind of question about transitioning between kind of the extremes. So sort of more looking at, okay, in general, brains want to be at the critical place, and I get that there's some difference between sleep and wakefulness, but then would it be fair to look at like rhythms of criticality, right? So the narrative arc of criticality and how it moves from probably slightly towards subcritical and then slightly towards supercritical? Or are the EEG measurements not sufficiently detailed to kind of give us that kind of data?
No, I think, well, so in the rat study we looked at, it was spike data, but just from the visual cortex, right? And I think that paper, if I understand your question correctly, was able to show
True, transitions,
the
yeah.
transition of criticality over time, right?
But
And
that's
so,
sort of a response to perturbation. What I meant was like a natural default mode rhythm that might exist with regards to criticality. And you get it in sleep and wakefulness by default. But do you get more like moment to moment kind of fluctuations that might be happening where people are moving between these two states, whether that be closer to, you know what I'm saying, as opposed to like hours, like 24 hours or 5 days?
well, within that rat study, I think each dot was a 4 hour period. And so they could track at a 4 hour granularity. I think.
But
Not
what I'm saying is you don't get enough fluctuation, right? You're talking about the perturbation one, right?
yeah.
Yeah, the
The
biggest thing is
no. I'm talking about the one where they just
the
measured
sleeping
sleep
one.
versus wake. Yeah, yeah.
Yeah, yeah, and they
Yeah,
do the
yeah, yeah.
REM. Yeah,
Yeah,
you're
yeah, yeah,
right.
yeah, with the REM and REM. Yeah, yeah, yeah. Sorry, yeah, yeah. Right. So the one where they occluded the rat's eye, um, they
It's
did
perturbation.
look incrementally at incremental changes, and I forget what the time window was there. So they were able to see incremental changes within a smaller overall time window.
Yeah.
Like if it was a 24-hour period, they had like pretty often they had a data point in that study in the monocular occlusion study. And they also did that in the sleep wake study. But both of those studies was an implanted electrode. So what they did is they implanted this electrode into the visual cortex, and then they like cemented it there so that the
Mm.
rat would like go about its daily life and stuff, but it had this electrode that was spitting out data like continuously for the whole time they did the experiment. And so it was able to do it, but it's limited to just the visual cortex, you know? And in animal studies, you could probably add, maybe like one, maybe two other like shank electrodes like that to get spike level, like neuron level data in the brain. So you could get like maybe two other regions in the brain. But it's a really complicated surgery every time you add another electrode into the mix.
Hmm. Hmm.
Um, and then the flip side is we do like EEG. Like EEG in humans, we can't do it chronically. We can only do like so long because the person like can't like stop doing their daily life to get high enough quality EEG that
Mm.
it's humans. It's a little bit less
I see.
realistic.
I see.
Um, but you can do like EEG in rats. Like there's a lab that can do like 32 channel like electrodes in rats. So they have like 32 chronically recorded. You could do that in a rat.
Okay, this makes sense. Yes, you're pointing out like potentially just like experimental limitations that hard limit. Yeah, yeah, okay, that's valid.
Yeah, but
Mm.
like, you can get longitudinal recordings in rats, I think, both at the, single regional level and also at the cortical level, but probably not at the same time. And that's
Okay.
the limitation is we can't do everything all at once. And also, I think a limitation is that for DCC, which is the measure used by a lot of these studies we saw in the presentation, DCC requires like at least an hour's worth of data, give or take, like 30 minutes minimum, but hours preferable to get reliable results, to be able to like spit out a reliable DCC number. Because like if you have too little data, you're not getting enough information that is required by DCC to give you its output answer.
Gotcha.
And
Yeah,
so that's a
yeah.
limitation in terms of how granular we can look at changes over time.
Granular is the keyword. Yes, granular. Yeah. Um, okay, moving to more like spurious thoughts, even more spurious.
Okay.
What if fluctuations in criticality was where first person time comes from?
Unpack that a little bit more for me.
It's just a crazy thought, but you can imagine like movements, like rhythms of criticality as the internal clock itself. I think might be an interesting idea because you have the clock on the wall, you have the sun moving around the earth. I mean, the earth moving around the sun. Whoops, and you get the circadian rhythm right of it. You have entrainment, and so on and so forth. But then there's such a thing as subjective first person time, and I just think it would be cool if there's some kind of rhythmic thing going on within an organism that generates a sense of the flow of time itself. If it were something like criticality dynamics, well, I don't know. It would be a cool story.
Yeah, I mean, so as a neuroscientist, right? Like I know that there's studies that look actually at how we do timing. Well, they look at how like biology keeps time, but most scientists stay really far away from subjective experience.
I
So,
know. I know.
right, so like
I know. I hear you. I'm just playing with ideas
no,
at this
no,
point.
no, no, no. I mean, I am the consciousness researcher, so I'm super on board with this. But
Okay.
I
Okay.
actually, I feel sort of frustrated, I think, with a lot of like perception scientists, for example, because people are like studying vision and they're like, okay, here's the visual pathway. We know all of this about the visual pathway, but it's nobody's looking at seeing. It's like, okay, like we can see
Hmm.
that this part of the brain is processing color, but it's not like,
Quality.
this is the set of things necessary to see color, right? Like, so in terms of this time thing you're bringing up, like there's definitely research that's looking into how like a set of neurons is able to keep sort of internal time.
Yeah.
But
But
that
yeah,
doesn't necessarily mean it's like the subjective time. And so
that's
if
what I'm saying.
like that slide I showed where it's like, oh, it seems criticality correlates with conscious experience, at least reportable conscious experience pretty well. It's not a bad idea, but I think it sort of depends on the fluctuations of criticality, right?
Right. Right. So yeah, just the spurious thought I had was, I don't know, like if you're doing a lot of criticality fluctuations, then your felt presence of time, like time speeding up or time slowing down, things are fun, things are boring, and so on and so forth. If those could be folded in, that would be a very neat story. And if the rhythm of criticality and the tempo of criticality, that'd be cool. If you had a paper called The Tempo of Criticality as a neural correlate of subjective time or whatever, that might be just, like I said, we only have
Pretty good
spurious
off the
ideas.
rip paper title right there. I mean that's cool. It's also like a testable hypothesis potentially, right? Like, assuming like in humans you're able to intentionally disrupt the criticality of the person without adding a pharmacological treatment,
Agent.
right? Like, yeah, agent, that's a good word. Right, yeah. So like with anesthesia pretty robustly decreases the criticality of the brain, right? But if you're anesthetized, like now you can't like do your experiment anymore about like, oh, like let's talk about your time perception, right?
Yeah, well,
So
just bore people. Just put them in a boring room, right? And their sense of time already, like you get time dilation already, and then just look at criticality. I don't know. If you could do the granular
no, yeah,
stuff,
that's
look at
testable.
fluctuations, and then,
Yeah.
and you show them
So
a really
yeah.
fun video, or you show them a boring video, and yeah, but I don't know. But I think like for AI, when I think about like AI and I think about developmental robotics, actually, this is another thing I wanted to ask you, but when I think about those things, like time being first person and objective and kind of like intrinsic is really crucial, right? And I think it's probably one of the most crucial things to nail down. As long as we have this external computer clock running, then I don't think it quite works. That's just a thought. Okay, and then you made a really cool point like before we spoke about the importance of plasticity with regards to like, and you used the word, what did you say? Something about the math. Like, why was that so obvious for you? I don't know if I'm saying enough words to jog your memory here.
No.
Like when we started talking and we talked about empowerment and then about the sort of plasticity leg of it, and you were just like, yeah, but the mathematical intractability of it, like on a long
Oh,
enough horizon and stuff like that. But it seemed quite intuitive for you. Like, why was that? Is there a reason, or just kind of
yeah, and I don't think we did that on recording, so maybe to help
no?
jog the viewers well, fill in the viewers is we were talking about, and correct me if I'm wrong, but what I'm hearing is when we were talking about, like designing robots and balancing between like the idea of programming everything into the robot so it's totally deterministic. There's no like nothing's left up to chance. There's no plasticity because you've coded everything to be a certain way and it's like all hammered out. And I said, well, that seems intractable because you can't program every possible scenario. There should be some learning that happens because it's unpredictable what things there will be. And if you program literally everything, that seems intractable because it's too much to
Yeah.
code.
All right.
Um, and this isn't, I think, what we were asking, but it might help illustrate for depending on which viewers we get, right? Like if you heard like the brain in a vat idea, right? Like, like it could be there's this idea in philosophy, right? Like we're a brain in a vat. And everything we experience is actually not really happening because we're just in a brain in a vat and everything's being like fed into our brain signals. And so that's why it feels the way it feels to be. Like it feels like we have a body and stuff, but actually we don't. We're just a brain in a vat. And so like, I think Daniel Dennett's the first person I saw have this counter to it. Daniel Dennett's a philosopher who's big in consciousness science and other science, but that's why I know him. And he was like, that doesn't make any sense because it's like impossible for it's like nearly impossible for that to be the true case that we're brain in a vat because there's so many possible sets of stimuli we can encounter, and so it does, like he said, intractable. It doesn't make any sense for that to be the case because there's too much inputs this brain in a vat would have to handle and be able to respond to and be able to code for and etc.
His argument was the brain in a vat is highly implausible because what? Because there are too many
because
inputs.
Because to successfully fool the brain in a vat into thinking that we have this rich experience and this body and this ability to move around and all of these things, it would require too much information input and too much speed of like responsiveness to be highly probable.
I see. Yeah, it's an argument about the improbability of it, and I think it's roughly the same thing about the simulation hypothesis.
Right.
I
Yeah.
I don't find those arguments all that fun. I don't know why people like can go on about that. It's just like, yeah, it's a possibility, but like there's so many like other fun possibilities too. That's the one you want to spend your philosophical time pondering. I don't know. It's okay. So okay, and then the last question is what excites you in like science in general or about criticality in specific, maybe your own research, anything. I know that you mentioned a few that were super exciting, but just like this is me attempting to steal your enthusiasm or your enthusiastic ideas so I can get a hint of what I should care about in the future.
Yeah, I mean, I think it's interesting. So criticality, at least in neuroscience, which is my field, right, is really gaining traction in wider amounts of researchers. So it's sort of gaining momentum due to this like this idea of it being a homeostatic set point of the brain, right? And that's showing up in labs that don't care about consciousness at all, and also labs that don't care about like wakefulness levels, you know. And then there's a separate group of neuroscientists who are studying like the wakefulness level indicator. Like, oh, like if you lose criticality, it seems you like lose the ability to move around, right? Um, uh, and also like as an indicator, like there's some studies that suggest like epileptic patients are super critical. So maybe we could use this as like a predictive tool, or if we could somehow measure the criticality of the brain, and if we notice it's falling towards supercriticality, that might be a flag that somebody's about to have a seizure, and so we can like be ready for this.
Right,
Um,
right, right. People with those conditions could have it on their Apple Watch.
yeah, yeah. So like these things, I think, are just making criticality interesting baseline to me. But the reason I'm extra interested in it is because as a consciousness researcher, like I'm looking for a reliable mathematical correlate of consciousness level. And so like that paper that I included in my presentation that was showing with like, if you recall, there was like the groups of human patients and they were under one of 3 anesthetics, and one of them, ketamine, the subjects reported consciousness while they were under the anesthesia. Like they were called having been conscious while they were under that anesthetic. And that's really cool because there's this problem in consciousness science about like, requiring behavior to indicate consciousness, or like assuming unconsciousness if there's no behavior. And this showed that this measure, criticality, correlates well at least with reported consciousness and not with behavioral responsiveness. And that makes it, I think, a promising tool. Obviously, it has the limitations of this study required some sort of behavioral response. They had to report consciousness to get this indicator, but I think it's a really cool start and like a place to leap off of.
Cool. Okay. Thank you. Thank you, Miss Jackson. Thank you, Hazel, for a wonderful talk. I learned a lot. I thought your explanations were super like clear. Yeah, I look forward to talking more as I do my PhD and you continue yours.
Yeah, thank you so much for having me, and I'm glad you got something out of the presentation. Like this was awesome. I'm glad we did it.
Okay. Thank you. Bye bye.
Bye.